my question is, I would like to design a Flex PCB. What do I need to know? You know how Flex PCB is made. How is it different from standard PCB?
Sure. Well, you know, the funny thing with PCB is that when you do a PCB, let's say you want to do a 4-layer PCB, the 4-layer PCB, whether it's a 4-layer or 40-layer, it's always made the same using the same process method. So 4-layer, whether 4-layer, 10-layer, 20-layer, 40 layers, it's always you have a core and you have a layer on both sides, pre-preg layer and a core layers on both sides. That's how the PCB goes. But when it comes to Flex, the funny thing with Flex is you can have a 2-layer Flex. You can have 10 different part numbers, and all 10 different part numbers could be totally different the way you set them up, right? So let's say you introduce a stiffener. You say, I want a stiffener on one, but on the next one, you can say, I want to plate it through holes, or plate it through a stiffener with plated through holes on it. Or you can have like, oh, well, I have a Flex with LED on it. So if you have a LED, or let's say you have a camera, you want heat dissipation. So you add, some kind of aluminum stiffener. So the material or the way you design a stack up for Flex circuits can get really complicated.
Okay. Now you mentioned a couple of times you mentioned stiffener. So what does it mean?
So a stiffener is basically a lot of time the most common stiffener we use is just your regular FR4 board. So you take a FR4 material, could be 370HR or could be something else. And what we do is we etch off the copper on both sides. And then in the end, you have something like this, which is just a piece of fiberglass material. And we attach it to your Flex. And the reason you attach it to Flex is a lot of times when you're attaching it, you may have some kind of components being soldered at that location. So if you're soldering a component, you want to make sure that there's some kind of rigidity behind that component, because if the component is on Flex circuits, and let's say the component is here and I bend it, it will end up breaking your solder joint. Okay, so you attach a stiffener just to add extra rigidity. So that's the meaning of stiffener.
I think very often you can find it where connectors are.
Yes. So, for example, I have this board in my hand, and there's a connector, and on the back side, I have a stiffener, just a piece of FR4. And that's exactly why we attach it. You have connector, you have any kind of soldering. When you're mounting components on your Flex, you want to make sure that there's rigidity underneath it. Otherwise, if you bend it, you will end up breaking solder joints.
What other words we need to know before we dive into this stack up? So stiffener, then I see Coverlay. What's Coverlay?
So Coverlay, Coverlay is unlike PCBs where you have Soldermask, which is a green color Soldermask or any other color. Soldermask is like it's a paste. It's a chemical that you apply for protection as a protective layer. In Flex world, we use Coverlay, and the reason we use Coverlay is because Soldermask, when you bend it, it cracks. Okay, so what we do is we use Coverlay, and Coverlay is basically made out of two different materials. You have Kapton, and then you have adhesive underneath it. So we use Coverlay instead of Soldermask because Coverlay is like a film. It's a material itself, not a chemical. So you apply on your PCBs, on your Flex to protect the layer and to add the flexibility. So on this Flex circuit that I have in my hand, I have Coverlay on both sides, and it's usually the brown color that you see. So I can bend it, but if there was a Soldermask, and if I bend it, Soldermask will crack. So that's your Coverlay.
And how do you make the openings in Coverlay?
So yeah, that's a good question. When it comes to Coverlays, there are things you can do in Coverlay, and there are things you cannot do in Coverlay. For example, if you have a circuit, a Flex circuit, and you want to mount a lot of components in that area, because Coverlay is a film, you have to cut bigger areas in Coverlay instead of Soldermask. Soldermask can handle very fine pitches. Okay, Coverlay cannot. So Coverlay we cut either using traditional routing machines or using laser machines. So let's say in our company, we have 2 laser machines. use a UV laser machine and just make a cut wherever you're going to place components. And let me give you an example. Okay, if I look at this board right here, what I see is a Soldermask, and I see Coverlay the rest of the area. And the reason is Coverlay, you cannot cut very fine areas. So the Coverlay has to be a big opening. So wherever we have components mounting, I open that area in the Coverlay and I apply Soldermask. But the rest of the area is covered with Coverlay.
So you still can also use Soldermask on Flex PCB, or this is like Flex rigid PCB, what you have?
Yeah, kind of. So if I look at this PCB that I have on the backside, so over here is green, on backside, it's a darker color. That's because I'm using polyamide material as a stiffener. So there is a bit of rigidity. So if I was to move this side, it's very flexible. But if I move this side, the green area is actually a bit rigid. Okay, so as long as there's a certain amount of rigidity built in, you can add, you can mount components. But again, the problem is, as long as not pure flex. So if I'm going to be bending, you can have components in the bend area, but you can have on the rest of the area.
I understand. This is, I already learned something new. See, I had no idea you can have Soldermask on Flex PCB. Just in the area where you would like to have the solder, ideally maybe you would like to use also stiffener on the other side.
Right. But mind you, this solder mask that we are using is not your regular PCB solder mask. It's a flexible solder mask. Okay, so it's a special solder mask for flex circuits.
But you still can make like smaller openings. So I don't know, 1 mil around the pad or something.
That's right.
Not 1 mil,
just like
maybe 3 mils.
Maybe 3 mil, yeah. So just like a PCB, whatever you do in your HDI PCBs with the solder mask, you can do the same thing. Unfortunately, on the flex, but unfortunately, the Coverlay, you cannot cut that fine, for the fine area. So that's why we apply solder mask wherever you're mounting mounting components, and the rest is Coverlay.
I understand now. Yeah. Okay, I didn't know you can really make small openings directly in the Coverlay. That's important to know. Okay, what else is here in this Flex stackup? You already mentioned adhesive, so so you stick the layers, you glue the layers together, basically. Right.
So let's say how you have in your PCB stackup, you have prepregs, right, between the different cores. We do the same thing on flex circuits, but the prepregs that we use, they're not really prepreg, they're special materials we use. So wherever you say prepreg, I wrote prepreg, but it's actually a special material, just like a prepreg, but designed specifically for flex circuits.
They call it PI or something like that?
Yes, PI. So you can see on my screen where I say 51N, that's a special material as a prepreg used, by, I think 55N is DuPont. I think it's DuPont. Okay, I can't remember. But I also mentioned adhesive when we were talking about Coverlay. So the Coverlay is made out of two things, made out of Kapton, which is the brown color that you see here. But in order for you to bond the Kapton with the flex circuits on top of copper, you need adhesive. So that's why when you, when you look on the right side where you say Coverlay, that Coverlay is actually two parts. It's Kapton and adhesive. Now the thing with Coverlay is you can buy Coverlay, which comes with Kapton and adhesive like as one material, or you can also buy just a Kapton and adhesive separately. Okay, so sometimes depending on the customer requirement, if we don't have the right type of Coverlay in-house, what we do is we always carry Kapton and adhesive separately as well, and we can use Kapton and adhesive together to make a Coverlay.
And in this stackup, what you have in this slide, there is no adhesive mentioned anywhere. So if someone needs, for example, like high-speed flex PCB or impedance control PCB, so how do you actually, how these engineers will specify this this stack up?
Right. So if you go on the materials website, whoever producing your material, or let's say you want to use a specific material you have in mind. Okay. When you go to the data sheet, it will actually specify. So let's say if you look up FR0110, it will show you it means a specific thickness of Kapton and specific thickness of adhesive. Right. So that's why I did not split it into Kapton and adhesive, because when I'm buying it Kapton with adhesive. So, but there are times when, you will separate depending on the needs. But if you were to look up FR0110, I'm sure you will see there are multiple variations of different FR0110 listed in the same area on the website. And they will not call 0110, they may call 0210 or something else. And each one of them will explain you the difference would be the thickness of adhesive and the thickness of Kapton. So you can have a Kapton 1 mil and half mil adhesive. You will have a different code instead of FR0110. You can have 1 mil and 1 mil. You can have half mil, Kapton and 1 mil adhesive. So you can have different variation, and you will see these different variations mentioned on the data sheet.
But I guess you have some kind of like your favorite stack ups, do you?
I would
so
like
it's
to
easy
say
for
yes.
you to manufacture it.
Yeah, I would like to say yes, but it's not really true, because as I said, every flex is so different than each other. It's hard to have a favorite, favorite stack up. But what I would say though is that we use DuPont materials more than anything else. I have another slide here. I totally forgot. Sorry, 1 second. Here. So these are the different materials you can get from DuPont. So you can see where I had FR4, Parallax FR4, the Coverlay. So this is the Coverlay it's referring to. So if I go to the website, I will see FR and then different codes, right? And when it comes to polyimide material, we use a lot of TK material. Okay, so TK material is, and we will talk about it in a second. No problem.
So this is kind of standard TK material, and
yes.
And the first one, Piralux,
Oh, sorry. Yeah, Parallax. That's the Coverlay.
Okay. I'm asking about this because I remember when I was designing for a flex connector, FFC connector or something, then they exactly specify the thickness, and they exactly specify the copper thickness and adhesive thickness and stiffener thickness. So I just wanted to know if it's possible to specify, this kind of very specific stack up which will fit exactly into this kind of connectors.
Yes, it is. It's a very common thing we do in Flex world when we're manufacturing. A lot of our designers will say, I want this specific thickness of Kapton and this specific thickness of adhesive, and we would go and find the right materials.
And what is like easiest way? So someone would like to manufacture in your company Flex PCB. What would be your recommendation? Like, I don't know, get the cheapest Flex PCB or get some kind of like safe Flex PCB, so they don't come up with materials which you don't use or which are very unnecessarily expensive to buy, for example. So where they should start,
Yeah, that's a good one. So I give you an example. Whether it's DuPont or Panasonic or Taconic or every company out there, they have some really high-end materials, right? They have, like, especially in the flex world, they have material which go up about 80 gigahertz. But the thing is, if a customer asks us and say, oh, well, hey, you know what, I want to use this, and that's fine, but a lot of time using these new material takes a long time for a flex manufacturer to get used to it or to learn how to use it. So I have been in situations where customer asks, oh, well, I want to use this material, but we ended up spending 2 months just to figuring out how to use that material. And a lot of time you end up failing. That's common. But in terms of which materials to use, which is the cheapest one to use,
I guess they should send you email or something like this.
Yeah, that would be the good start, because I don't want to use the word cheapest, but because currently in 2022, the money is not even the issue. The issue is the lead time for material. So when I say Parallax TK, that's like the most commonly available version of DuPont material that I can get. So we use a lot of TK and AP. Okay, so I cannot say the cheapest, because if you look at the cost of the material, it's not that much. Like you can have a material for $1 per square feet, and you can have another material for $2 square feet. But manufacturers make the boards in a panel form, so they would usually run 12 by 18 panels. So the material cost is not that much. It's the cost of processing that adds a lot of cost. But the lead time is a big problem. Like there are a lot of materials out there which are exactly what customer needs, but the lead times are like 25 weeks or 30 weeks. Here's the thing. I guess every company is a little different. Like our company is mostly medical devices. So when we do medical devices, we're going to be doing production runs, not prototype. So we spend a lot of time designing stack-ups with the customer.
I guess you are careful about like reliability and longevity and this kind of stuff, because
that's right. Because as I said, we are mostly medical. So what happens in medical is, once you build a product for a customer and once it gets FDA approved, you're going to be making it for 10 years, and then those boards, you have to give warranties and guarantees that on their reliability, because a lot of times it's a life-saving device or something like that. So yeah, that's why we are careful. But
so there can be differences. I'm sorry for interrupting. There can be differences in quality of Flex PCB.
There could be, yes. I mean, we face this issue all the time where what happens is, customer may be saying, hey, use this Flex, use this design, and we had it made somewhere else. But that when they had it done somewhere else, it could have been just a quick prototype, but when you go in production, it may not be the best suited material. Right? So that's what I'm saying, we need to differentiate between the prototypes, production run, and we need to spend some time understanding which is the right material for your use, for your needs.
So is there something else what we should mention in these materials? Like, can you click back on the stackup? We covered stiffener, Coverlay.
We can cover.
Foil. We didn't talk about copper foil.
Sure. Okay.
So
sorry, give me a second.
Okay.
Yeah.
How thick copper can we use?
Okay. So this stackup is actually a stackup for a rigid flex board. Okay. So the left side is actually a rigid, and this side is the flex side.
Rigid, it means standard PCB.
Yeah, a standard PCB. So you have the flex layer running inside your PCB. So this area on the left side is actually the PCB itself, right? So the copper plating and copper foil that we're referring to your standard copper foil for your PCB, not the flex. So, if you're using a copper foil, you can use 1/2 ounce, 1 ounce. I mean, 1/2 ounce is like the most common version that we use. Sometimes customer want like really fine pitch on the PCB side, then we would probably use 1/3 or maybe 1/4 ounce as well. But I would say 1/2 ounce is pretty standard. And the reason is, a lot of time, when you're doing PCBs, you can have HDI stuff. So if you're doing HDI, or if you're doing micro vias or micro via filling, blind vias, then you would probably end up using 1/3 ounce or 1/2 ounce. Oh, sorry, 1/3 ounce or 1/4 ounce. Okay, because you want to start with the thinnest possible copper.
And we are talking only about the material, or are we talking about material plus plating?
We're only talking about the material.
Okay, so there will be extra plating on the top.
Right, right. So, you know, that's why when you have HDI board, you start like 1/4 ounce or 1/3 ounce, because then you will add plating in the micro vias, and then you planarize, you add more plating. So that plating adds up. When it comes to rigid flex, as this stackup is, I would say if it's a rigid flex with HDI technology on the rigid side, then you would probably start 1/3 or 1/4. But if it's not, if it's a standard technology, then 1/2 ounce is the way to go.
Is it going to influence how reliable the flex is? For example, can you use 2 OZ?
Can we use 2 ounce? Is that what you said? Yeah. Yes, you can. That's, you know, it's not affecting your flex, because the material for flex is the material for flex. So that's a separate issue. So if you're using a PCB with thicker copper, that has to do with the PCB side of it. So it's not going to affect. But when it comes to flex, and if you ask me what kind of copper we want to use on flex, right? We use 1 ounce and we use 2 ounce here and there. Sure, no problem. I even use a 7 ounce and 14 ounce. It depends on the application. And I will show you in a bit, you know, for example, this one right here is a 10 ounce flex. It's a flex, but it's 10 ounce. But generally speaking, when you do flex, we like to stick with 1/3 ounce, because you want the flexibility, you want the bendability. The thinner the copper, the better it is. So we use 1/3 ounce quite often on a flex, and 1/2 ounce. 1/3 and 1/2 ounce is very common. Okay, but on a PCB side, usually 1/2 ounce, 1 ounce, and if you have a power plane, so you know you can go 2 ounce.
Okay. I was just curious, you know, if there is like limitation because of the flexibility or because of cracking, or I don't know what could happen if the copper is more, or if it's thicker. I've seen you could like kind of bend it, and it just stayed bended when it was like too thick.
Right. But that's why I'm trying to separate the PCB part from the flex part, right? The PCB part, you can have 1/2 ounce, 2 ounce, whatever.
I know what I mean.
But the flex, the flex part, I mean, let me give you an example. I have a flex here. I have a flex, and what it is I have a flex with the green area, so you can see, you know, it's a Soldermask. Yeah, but there's no stiffener. It's actually also a flex. Okay, it's also flexible. But the rest of the flex is much thinner. However, this is not 1/3 ounce. This is definitely 2 ounce material right here, and 2 layers. Okay, so there are, I mean, yes, when it comes to, you know, you can have cracks and all that, but I mean, that's where the knowledge comes in. It's your copper doesn't just crack as long as it's under your Coverlay. That's why you apply the Coverlay, so you don't crack. But you can have cracks. A lot of time the cracks are when you have the FR4 on a rigid flex and the flex, and where it's joining to each other. When you bend it, you can have cracks over there. That's a very common cracking point.
So how do you prevent these?
Yeah, right. So these are called stress points. And there are a couple of ways you prevent this. One way is you apply what we call strain relief. Okay, strain relief is an ink. Sorry, just give me a second. So I have this rigid flex, and I don't know if you can see or not, there's some kind of transparent ink applied at the junction right here. And what that is strain relief. Some people call it echo bond, which is not the right word. Echo bond is it's not a process. It's a material itself. The process is called strain relief. So what you do is, here's a good example. You can see the white ink. So this is a very flexible ink, and it takes away the extra force that we will be exerting at this stress point. So by doing that, you take away a bit of force.
So basically, so that's the one way. PCB is not bending directly where the edge is, but
right.
the forces are kind of spread in large area.
True, true.
Okay.
Yeah, that's exactly how it is.
I didn't know about this technique.
Yeah, right.
See,
that's
I'm
one,
learning.
and...
I just learning. I had no idea this can be done.
Right.
Again, how is it called? So
it's called. Some people call it echo bonding, but it's not the right word. The right word is strain relief.
How do you?
So you are.
Go ahead.
You want me to write it here?
No, it's okay. How do you specify this in your manufacturing? Yeah, exactly.
So you know, if you are a designer, you can say I want a strain relief applied to all these points. If you know if your product is specific to specific application, then you can either do your own research and find out what strain relief is good for you, or you can ask your flex manufacturer, hey, you know, I want to apply some kind of strain relief. Which one do you recommend? That's one way of doing it. The other one is maybe your product is not really that complex, or let's just say you're not too worried about which type of strain relief. Then you can just go to your flex and say, just apply a strain relief, and they will do whatever. This strain relief comes in multiple colors. It comes in this whitish color. It comes in black as well. And it also comes in transparent. Okay. We use mostly strain relief by 3M, okay, 3M company. EcoBond is an older product. We also use a lot of EcoBond as well. EcoBond is an older product. 3M is a bit newer, but both are great, and we use both of them as strain relief.
Okay, but very often I don't see this on Flex PCBs. So are there some other techniques which would help prevent the cracking in these places?
There are some other as well. One of them is making sure that your stiffener is not too thick. Okay. Like where you have a stiffener and you have the flex together, you just want to make sure it's not too thick. But that being said, I mean, that applies for if you're just applying a non-plated stiffener. But if you're making a board like this, there's nothing you can do. I mean, that's the way it is.
I think I read also you can use some. So when you are coming out of this rigid PCB, then you don't go straight. Maybe you make corners a little bit rounded or something like this. Is this kind of technique what you could use?
Yes, I think I have a slide on it. Let me just check. Here's a slide, but it's not the exact same slide. Sorry, but I know what you're saying. Something like this. No, not exactly. I know what you're saying, and that is when you have a sharp angle. When you have a sharp angle, you kind of like, I don't know how to explain it. You kind of like give it a fillet. Okay, give it a fillet, and that helps reduce the stress.
That's
as well.
What I meant. So you just
yes.
You just make it, I don't know, a little bit rounded or something. The exit is a little bit rounded.
Right at the junction. And I actually have a fillet here, but it's so small you can't see that. Right. So that fillet is one way of making sure that you're reducing the stress as well.
But it's not like, is it necessary? No.
No, it depends on how you're going to bend it. I mean, having a strain relief is really good because you're bending it this way, but unless you're going to bend it at an angle like this, then the fillet will come in more handy. In this case, fillet is not going to do much because you already have strain relief applied.
What is the smallest area what you can bend? You know, how much space you need to be sure that you can bend it, I don't know, forever and not only twice? So,
right, we're talking about bend radius now, right?
Yes.
Okay, let me go to the bend radius. This is a slide for bend radius. Okay, so the rule of thumb is whatever the thickness is, the thickness of your flex is, the bend radius should be at least 10 times than the thickness. Okay. So the bend radius, if I have this as 7 mils, so it can only bend at 70 degrees. Okay. But it also, it's hard to explain because sometimes it's not just the bend, you're talking about how tight is your radius, right? How tight. So that's when, your, this thing comes in where you have minimum 10 times the thickness. But some people say 10 times, some say 12, some say 8. That's debatable. Everybody has their own way of looking at it. I think there's a reference in IPC specifications as well. And I think IPC specifications say 10 times, but I'm not 100% sure. I think that's what it is, but I'm not 100% sure. But we suggest 10 times.
Okay.
Now, there are other things to keep in mind as well. It's not just the 10 times like this. I was actually listening to someone else's presentation on Flex, and I know they mentioned that if you have number of layers, and they were looking at it from number of layers, like how many number of layers you have, that also changes your bend radius. So it could be the number of layers, it could be the bend radius, like in terms of the thickness of the flex. It could also be if it's a rigid flex or just a flex. Okay, but to keep the conversation simple for now, I would say 10 times the material thickness is the bend radius. Okay.
I wanted to mention this so everyone knows that they need to add this to the length, or they need to be sure there is this kind of safe length to to keep the do not damage the flex. That's what I mean. And I noticed this picture, like never put a via in bend area. So are there some restrictions what should not be in this area which is bending?
Yes. So you cannot have any vias in the bend. You cannot have any components in that bend area because, of course, if you're going to bend it, and you can see there was a via. Well, I mean, we bend the flex at the via just to show how it works, and we took the cross section. But yes, you cannot have vias because when you bend it, you have plating inside the vias, and that will crack. Okay, or any sort of plating. And also, if there's a via, you will end up damaging the via. But also, there are other rules such as if I'm bending this flex, how far can I from the bend can I mount my components on the flex? That's another rule. I believe we usually go by 50 mils. So if I say this is my bend, and if this is my bend area right here, so it has to be minimum 50 mil away from the bend areas where I can mount the components. And that number, the 50 mil, can change from different flex manufacturers and between different flex manufacturers, and also could be a design dependent as well.
And I guess so maybe you don't want to do any right corners in these areas, or
yes. When it comes to right corners, here's just a design guideline for what you can do on the flex and what you shouldn't do on the flex when it comes to designing.
So this is general. This is not only in the bending area.
No, this is general. But in the bending areas also, I mean, you don't want to have right corners. Yes, you're right. You don't want to have right corners on your traces in the bend area, for sure.
Okay, so on whole Flex PCB, ideally maybe use rounded corners, because I guess it may crack exactly where the corner is if it's right angle or something. Right,
and it adds more stress. So if you do a rounded corner, you're taking away the stress. Yes.
Okay. What about these teardrops? Do you add the teardrops, or PCB designer has to add the teardrops?
So this is simply showing you how it should be done. So if a PCB designer can do it, great. If not, then we do it ourselves. Pretty much all flex companies would do this as a standard if the designer hasn't done so. Now, it's up to the flex manufacturer, the engineers, to go back to the designer and confirm with them that that's what we are doing, just so that designer is aware of it. But yeah, you're right. I mean, you have to do this. You have to have these teardrops on your design. Who does it? It doesn't matter. I mean, if you did it as a designer, it's less work for me.
Because I've seen like some software may not support it, for example.
Right. Yeah, that is true. But the good thing is, so the PCB manufacturing companies or the flex manufacturing companies, the softwares they use to edit your data or edit your Gerber file, they are more than capable of adding teardrops. So if as a designer you cannot, your flex manufacturer should be able to do it themselves.
They do it automatically, or you have to ask for it, or?
Well, I would say the best way to do it is if the flex manufacturer is changing your design, they should always go back and tell you that, hey, I need to do this on your design for this reason, because that is a good practice. So if somebody does it and don't tell you, they may be doing a good thing to your design, but it's your design. It's my responsibility to come back and say, Robert, you know what? I want to make this change on your design. So I would say in most cases, the manufacturer engineer will go back to the designer and say, I would like to make these changes.
Because, this is not only a question about flex. I've seen also standard PCB manufacturers, they very often add teardrops because it will improve the I think reliability or lower the weight of the PCBs. I don't know, because of the drilling. I don't know exactly, but I think that's also a reason why these teardrops are used, because of the accuracy of drilling, for example. Correct? Yes,
and we can talk about it. In PCB world, whether it's PCB or flex, let's just combine them together for a second. So let's say you have a hole which is, and you have a copper pad which is very, very tight, meaning on a PCB. Sorry, I got cold, so
it's okay.
I'm suffering. So let's say on your PCB you have 10 mil via. Okay, and you have a copper pad, 20 mil copper pad. It's kind of tight for a mechanical drill to drill 10 mil via on 20 mil pad, because your PCB manufacturer will probably add a little bit of, because the 10 mil via is your design via. So the PCB manufacturer will need to compensate it for copper plating, right? So they will drill the hole a little bigger. So let's say they're drilling it at 14 mil, or even 12 mil, now you have a 20 mil pad, so you have 4 mil annual ring per side. So, and the drilling machines, they usually have, I believe, a plus minus 3 mil tolerance when it comes to positional drilling. So if I want to drill a hole here, my drill bits can go left, right, anyway, 3 mil. So if that's the case, we would like to add, a PCB manufacturer like to add this teardrops, because in case your drilling ends up cutting the trace and pad junction, you actually have this teardrop and you can still meet the class 2 or class 3 requirements, right? That's one. The other thing is, if you're using an immersion silver finish, immersion silver tend to attack your copper, so it tends to come in and eat up the copper a little bit. Okay, so a lot of time you will see the PCB manufacturers, what they do is anytime you have immersion silver, they will add a little bit of extra copper at the junction. And I've worked for some other companies in the past, and different companies have designed a different shape of these teardrops, specifically for immersion silver.
I didn't know that.
Okay, so there are companies out there, they may not be using these standard teardrop, they may be using a different shape of a teardrop for immersion silver only.
What do you have on this right side of the page?
Yeah, so this is just explaining you when you're routing your traces on your flex circuit, how you should route it. So like on the right of it, it says not preferred. So you don't want to make these angles. Instead, what you want to do is you want to do these round angles. Same thing here. I mean, this is okay. So instead of doing this, this corner that you're creating, you don't want to create this corner. If you are going to keep this corner, fill it like almost like a teardrop, but not teardrop, but the fill it so you have a rounded corner. So that's what it's referring to. You want to avoid these corners. There are two reasons for avoiding this. So you don't want to do this. You can do this instead. The two reasons are, and this is not just for Flex, it also applies to your PCBs as well. Okay. Two reasons are, for Flex, the reason is you want to avoid as many right angles or as many angles as possible. You want to have round because you will be bending the Flex. That's one reason for Flex. And the common reason for Flex and PCB is that when the PCB manufacturers or the Flex manufacturers doing their chemical processes, what happens is chemical goes there and ends up getting trapped in these angles. So that ends up affecting the quality of your PCB or Flex.
Is it still the thing? Because I heard now it's not so bad as it used to be. So
it's not so bad, but a lot of time, the PCB manufacturers will actually fix these corners, and they may not tell you because they're fixing it so small, then you may not even be aware, because it's like there's no need to tell the customer because it's just a minor fill. So they may not be coming back to you and advising you that this is what they're doing. But yes, I mean, the problems are solved, but there are always little problems.
Okay,
so this is just, this is all I'm saying is this is a good way of doing it. If you don't do it, it doesn't mean that your design will be bad. It's just a preventive way. It's a way of making sure that no problems happen during the chemical process.
From my view, it's like better the designer do it, then less changes PCB manufacturers have to do in the PCB.
True, exactly.
So designer knows exactly what will be manufactured.
That's right.
Okay, what about the other pictures on the bottom?
So other picture, again, it's a teardrop. You can see this one has no teardrop.
No, this on the right.
On the right?
Yeah.
This one right here. Okay, so you can see in this one, you have more gap and less gap in these two. So this is basically what it's saying is, instead of doing this, you should space out equally. Okay, and this doesn't just apply to Flex, it applies to PCB as well. I mean, I see a lot of time, you may have like 10 lines running in parallel to each other, and every one of them is a little bit off than others. And what happens is, if you're dealing with a really tight spacing, let's say 2.5 mil or 3 mil spacing, the PCB manufacturing engineers or CAM engineers, they end up fixing these, moving these traces 0.5 mil up and down.
Really?
To create that minimum. Yeah. Not necessarily all of them, but let's say you're below the manufacturing capability, they will end up doing this. Okay, and I used to do that. I mean, I used to be a CAM engineer a long time ago. So I used to do that. I used to hate doing it because it's a very manual process. Okay, so I would move the trace by 0.5 mil and kind of like get that extra spacing that I need to make the design manufacturable. The difficulty is really when it comes to spacing. So, if you ask me, can you do 2 mil spacing and your copper layer is 1/3 ons? And I may say, I can do 2 mil spacing, but that could be very design dependent, meaning if you have only few locations where you have 2 mil spacing on 1/3 ons, I may say, okay, I can do it. But if it's many locations, then I may not be able to handle it. And if you have a pad and you have a trace running beside it, and you say it's only 2 mil spacing, it may be okay. But if I have two very long traces running parallel to each other with 2 mil spacing, that may be hard to handle.
Okay, I understand.
So that's why I was referring to spacing them out.
And again, I guess these two pictures are same about spacing.
Pretty much, yes. Yes.
Okay.
Yeah, so you can see this is too close. It's saying, you know, instead of running it, just make it more spacing. That's exactly what it's saying. Create more spacing if possible.
So what are some other recommendations for doing PCB layout for Flex? What is like different from doing PCB layout between standard PCB and Flex PCB?
Sure. Let me share with you different. This is the one which is a little different than PCB versus Flex. The one on the left is we already talked about it. Yeah. This is a little different. What this is saying is if you have Flex, okay, if it's very thick Flex, it doesn't matter. I mean, but a Flex where you will be bending, a bendable area, what you want to do is you don't want to have traces on the layers beside each other where traces are right on top of each other.
Yeah, like, so if I have the right picture, correct?
Yes, you don't want that. Yeah. So you want the left one. So you want to, if I have 4-layer Flex, the layer 1, if I have a trace here, the layer 2, the trace should be a little bit shifted. Right? That's what you need to do.
What is the reason?
The reason is when you're bending in coppers on top of copper, you want to have a little bit staggering. Okay, you want to stagger them so it gives you more flexibility.
Okay, what else?
The bottom one is a very interesting one. So let's say you have these gold fingers, for example, right? If this was a PCB and this would be Soldermask opening, you would be opening Soldermask for the all of these fingers, right? So your Soldermask opening will be larger. As a matter of fact, if these are gold fingers, you wouldn't have a Soldermask opening for each pad. You will do a gang relief.
Yeah, I think you do it same way also for standard PCB very often.
Right. So you would have a gang relief here. On the other hand, no, Soldermask is a chemical, but Coverlay is a film. So what you do is you bond Coverlay with your Flex, so you're bonding it. It needs to add extra strength for bonding. So in a case like this, the film is actually covering the fingers a little bit. Okay? You see this area right here? So all this area right here is Coverlay. Yes, it's Coverlay. So this is the open area.
Yeah, that's what confused me. Like,
right.
I was thinking the open area is the white area.
Yeah. Right. So no, this is a Coverlay. So you're using a Coverlay to cover the fingers so that it has a more better bonding adhesion there. So that's something we do, you know, in Flex world.
So this would be this would be used, for example, when the Flex PCB is plugged into a connector. So if you would like to create this kind of contact.
Yes. Right. So you would, as a designer, you would need to take that into account, that we would be covering a little bit. So your finger should be long enough where your Coverlay is not going inside the connector.
I understand. Okay.
Right.
And I think there is also something with stiffener in these areas. And I've seen picture. You have picture about the next slide. Yeah, that's exactly what I meant. Yeah.
Right. This slide. So yes, what it's saying is, let me move this. So it's saying stiffener and Coverlay termination line should overlap minimum 12 mil to avoid stress point. So let me see if I have.
Yeah, on the left, I can see it. On the left picture, stiffener is longer, so it is also a little bit in same area where the Coverlay is.
Right. So if I have if, you know, let's say, you know, I have a Flex, and on the Flex, I want to have some components on the top side. On the bottom side, I got to have stiffener. So that that area has to be open with Coverlay because you're going to be doing soldering there. So you need to have it open. So the Coverlay, the stiffener has to cover the Coverlay. That's what it's saying. So it shouldn't be like, oh, so this is my stiffener and this is my Coverlay facing each other. No, it should be a little bit overlapping to ensure that, there's a good bond.
Okay, now I have a question. Do you place stiffener on top of Coverlay?
We do. Sometimes we do, yes. So it depends on your application or how you're using your Flex. So if you're going to be doing some kind of assembly and you're putting a stiffener on the other side, you will not have Coverlay, right? Because that's the open area. But you can also have stiffener on Coverlay as well.
Okay.
Yeah.
How do you specify?
That's very good.
How do you specify these areas in documentation?
That's a good question. I don't know. I mean, stuff like this is usually common that the Flex manufacturers will do. So a lot of time designers don't mention that, and we will do it and go back to the designer and say, hey, look, you know what? It has to be overlapping a little bit. But when you are designing it, and I have seen drawings or Gerbers from designers where what they do is they will open the Coverlay and they will say on the not sill screen, but like kind of like a DXF file or something, they will say these are the dimensions for Coverlay openings and this is the dimension for stiffener where it's supposed to go. Right? And so, a lot of time, sorry, go ahead.
No, go ahead. Go ahead. I will remember.
I was going to say a lot of time what designers do is on their sill screen, they will actually mark where the stiffener is supposed to go. So it's not just the DXF, but they will mark on sill screen, you know what, here and here, these are the lines, that's where stiffener is supposed to go.
Okay. So, now I have another question. I have to remember the first one. My second one is, you mentioned sill screen. So so you do sill screen on top of Coverlay, or you do it also directly on the PCB or on stiffener or
on the Coverlay?
Okay. Okay.
Sorry.
And my previous my previous question is then, so basically when you receive documentation to manufacture Flex PCB, then there will be standard copper layers, and then there will be a layer for Coverlay, there will be layer for stiffener, and that's how it works. Okay, so layer for stiffener, there is just, I don't know, square, and it says like here will be the stiffener or something like this.
That's right. You would say the thickness of the stiffener you want. So you would have to specify the thickness. And you would, just like you will say, oh, well, this is the location where I want the stiffener. Here are the dimensions X and Y, and here's the dimension for the stiffener X and Y. Okay. We have customers who like to sometimes identify what type of stiffeners they want. So it could be, regular. Generally, we use regular FR4, like any of the 370HR as a stiffener, but depending on what the application is, you can have different stiffeners.
I heard you can have like aluminum stiffener or...
Yes, you can have an aluminum stiffener, and you use aluminum stiffener for heat dissipation. So I have this Flex, and I have a camera and LED right here, and on the back side I have aluminum stiffener. And the reason is, over here you will produce heat, so you want to remove the heat, dissipate the heat, so you use aluminum stiffener.
Do you connect this stiffener somehow together with the PCB, or heat just transferred through the PCB?
Well, there's no Coverlay in this area. So you won't have Coverlay. You will just have a copper layer, and you will attach this stiffener to that copper layer using some kind of adhesive.
Is it
thermally bonded?
And the adhesive is non-conductive then, or you can only stick it on like a solid ground plane, for example?
You can.
But you should not place this aluminum stiffener on top of multiple tracks, different tracks, correct? Because that would short them?
Yes, that's right. Well, I mean, you would have to open the area where you want the connection in the coverlay. So it's not like you can just open so you just have to open the areas where it's connecting to dissipate the heat. But you have to be careful you don't end up shorting other traces. Yes.
Yeah.
Yeah. So that's something you would have to do. Yes, in your design.
Okay. Interesting. Are there some other materials for stiffeners?
Yes.
Steel? Is there steel or something?
There is steel. I don't know if there's some kind of there's copper stiffener. You can use copper. You can use aluminum. I have heard there are steel stiffeners as well, depending on the application you're using it. But we use polyimide stiffener a lot as well. Okay, let me give you an example of polyimide stiffener. So this board right here will have, some kind of something mounted here, and at the back there's a polyimide stiffener. You can see the color difference. So you have a polyimide stiffener.
So what's the difference between polyimide and FR4?
So the polyimide is the material you use to make flex. So sometimes you're not using your regular FR4 stiffener, you're using a polyimide because you may be bending it a little bit. So if you need a little bit of bend, because there are no SMT components here, these are going to be hand-assembled through-hole components. Could be a connector or something, right? So in that case, maybe polyimide stiffener is good enough. And maybe you need a little bit of rigidity. That's, a little bit of flexibility. That's why you use polyimide stiffener.
Okay.
Yeah.
Cool. There is so much information about all these materials and how to arrange everything. So what
I'm
else?
still learning myself.
What else do you have on these slides? Let's have a look.
Sure. Okay. Let me go to, let me go to stiffeners right here. I have all the stiffener mentioned right here. It's also, there's a good point I want to cover here. A weir should always be placed at least 20 mil from the stiffener edge. Okay. That's a rule that as a designer you should
from the edge,
follow.
that's the important word. So you can place it where the stiffener is. You can place it outside of stiffener, but not on the edge.
Right. Okay. So if you're placing it outside the edge, you got to make sure it's 20 mils outside the edge. Okay.
I guess it's very similar to the rule you don't want to place vias where the cable will be bending.
Right. And there are a couple of things I want to mention when it comes to stiffener. There are different types of stiffeners, yes, but even when it comes to FR4 stiffener, you can have a stiffener, you can like drill hole. You can have a stiffener just like backing up something. You can have stiffeners with the holes in there. So you may be stiffening it because you have a through-hole component that you're putting in and you're soldering. So you can have that. You can also have the stiffeners with plated through holes. Okay, you can have a stiffener with plated through holes. Like for example, the first one, it says right here, the stiffeners can then be lined up with the plated through holes in the flex and the connector then solder. Now this could be this could apply to your stiffeners with holes with no plating, but the holes with plating as well. The thing is, when you have a stiffener with holes which are plated, that's a double-sided board, the stiffener itself. The only way you get plated holes on a stiffener is if you're taking an FR4 board and you're running it like a double-sided board through your process and then removing all the other copper. So having a FR4 stiffener with the plated through hole is like making a flex circuit, making a double-sided board, and then you're attaching each other. But there's a cost involved. That's what you got to remember.
But theoretically, you don't need it. You can just use the copper on the Flex PCB and go with the pins through the stiffener.
Majority of the time, yes, that's exactly the time. Yes.
But in this case, components, through-hole components has to be placed on the side where the stiffener is, and pins go down to the area where the flex is. You can't do it the other way.
You can do either way.
But then it will be more expensive.
Yes, it will be more expensive. That's true.
Okay.
True. So I have an example here. So you can see this is a flex, and I applied a regular FR4 stiffener. And
that's
then
exactly
these
what
leaves, yeah, right. This is the right way of doing it. The other way is it's just expensive.
So do you need to like specifically say drill the holes through the stiffener, or it will be done automatically? I think no. You have to say this, or
not really. All you have to say is at this location I want a stiffener. All you have to say is I want a stiffener which is this thick, and this is the dimension. And the PCB manufacturer will know because you're going to tell them. Oh, okay. Sorry. Let me clarify one thing. If you're making your flex at a company which doesn't do assembly, okay, which don't do assembly, so you're going to send this company, hey, make a flex for me, and you're going to send it to another company to assemble it, then you need to tell them, oh, there's a hole and I need, I need the company.
That's what I mean, because normally they would drill through the flex and make the flex and then stick the stiffener with no holes on it, correct?
Right. And so like, here's the thing with flex companies. A lot of flex companies actually assemble their own flex. And the reason is assembling the flex is not same thing as assembling your regular rigid PCBs. So that's why, assembling flex is quite complicated. So that's why a lot of flex manufacturers offer flex assembly as a service. So if you were to go to these flex shop and say, hey, make me a flex circuit, and they would kind of know, okay, so we need to put the holes
because there will be components. Yeah, they know. Oh.
Right. And they would know. But you're right. I mean, the best way of designing flex circuit is if you have a stiffener, you identify what hole size you want. That would be the best way. Yes.
This is interesting because it looks to me like there is no really standard for the documentation to manufacture flex PCBs.
Yes and no. I mean, every flex company I know, they have their design guidelines. So we have our own design guideline as well. But the flex is just so many things happening. But you're right. I mean, you can have a design guideline and still end up missing a lot of things.
Okay, what else do we have here?
This is too much reading here. I'm not going to read too much, but this is example. So when you have a flex, and what we do is we like to add these little holes or circle, whatever you want to call it, but they take away the stress. So they add to the bendability. Okay. So, excuse me. We probably wouldn't do
flex is the colored area, correct?
Yes.
Okay.
The Coverlay area, the brown area.
Okay.
So, well, the white area is also flex, but there is no copper. It's just part of the flex. There's no copper.
Okay. Okay. So this is we are talking about copper.
Right. So there's yes, we're talking about copper. So there's no copper in this area. So this is your copper. That's
copper. The corner of a, I don't know, ground plane, for example.
Right. Let me give you an example. So I have this board, okay, and you can see we added a stress. We added this hole right here. So it adds, extra bendability because it takes away the stress.
Okay, I understand.
So obviously, if you have traces and some other component, you can't do that. But when you don't have something like that, you can. So in this case, by adding these two holes, I can do a lot more. I'm taking away the stress from the stress points.
And I guess this would be the place which would start tearing, probably if there is no this hole.
Yes, could be. So these are the stress. There's a stress point, and when because that's where the bending taking place. So if you drop this hole, it makes it more flexible. Okay, well, it doesn't make it more flexible. It just takes away the stress.
The stress is kind of spread around the hole.
That's right.
I guess.
That's right.
It's not in one small corner.
That's right.
I didn't ask, or I haven't asked yet about ground planes, because I heard that you would like to use maybe this hashed ground planes, but then other people told me sometimes it may not be necessary, because if you need to bend it, I don't know, a couple of times, then you can just use solid ground plane and it's going to work perfectly fine.
Right. So the ground planes we use for shielding, right? You want to, for EMI stuff. So you can use solid ground planes, yes, and you can use crosshatch copper planes as well. Solid planes are okay. There's nothing wrong. For a very long time, we use solid planes. I have like lots and lots of flex circuits on my table right now. They all have solid planes. So you use solid plane as a default, but you use crosshatch when you need to. Not everything needs to be crosshatch. The thing with crosshatch is crosshatch will add to your flexibility. So if you have a circuit board where you don't care about bend too much, then you're okay with copper plane. So the one that I showed you before, like this is pure copper because it doesn't need to be flexed too much. But if you need really flexibility, a lot of flexibility, then you would consider crosshatch. Because when you do a crosshatch, let's go to this one, these areas right here are not copper, okay? So you're actually adding flexibility. So that's when you use crosshatch. And also it affects your impedances as well. Crosshatch, so when we calculate impedance on flex circuit using, let's say, polar, you have an option for crosshatch. So you got to make sure you're using crosshatch if you have crosshatch planes. If you don't have crosshatch plane, then you just stick with copper plane. So it's not necessary, but yes, you can use crosshatch. So let me give you an example. I have this circuit. I don't know if you can see the crosshatch on it. Can you see the crosshatch?
Maybe.
Probably not.
Is it like super? Yeah, I can see it now. Yeah, I can see it.
You see the crosshatch, right? So this is designed because this flex circuit will be bent a lot. So having a crosshatch definitely helps with the bendability.
So how many times can you bend it if it's solid?
I don't have an answer for that. I really don't know. Sorry. I think it depends on the design itself. Like it depends on what exactly are you doing. Like first of all, how many layers are there? If there are traces inside, and when you're bending, how your bend radius and everything. But I don't have an exact answer on how many times you can bend. I can find out and can come back to you later. But
so I would maybe say, if in your application you just need to bend the PCB to mount it into enclosure, then you can use solid. But if it's going to be, I don't know, camera which is going to move constantly, then maybe you would like to use hash.
True. Okay. So I just did a design for one of our customers, and they just wanted to use the PCB as a bus bar between two PCBs, the flex between two PCBs, and it was a high copper, so it was just pure ground. Yes, you're right. If you're going to be bending a lot, then it's definitely better to have a crosshatch. I have this flex circuit, a rigid PCB, and it's all ground on both sides, because the idea is it's going to stay in some kind of shape.
This is good to know.
I would say that, but I really don't know the exact number.
But this is good to know, because I was worried before I read somewhere like you can't really use solid ground planes. But then someone, I think Rick Hartley or someone else told me like, no, you can use solid ground planes on Flex, and I was like, oh, I didn't know that.
You can actually. A lot of the stuff that we do is solid ground planes. Yeah.
Okay, and you started this shielding. I've seen you have a couple of slides about shielding here.
Yes. So the silver paste epoxy was used as a shielding for a very long time. We would just apply the silver epoxy as a shielding material.
So you kind of like cover a whole Flex PCB with I don't know,
with the
silver foil.
Yes.
All right.
Yes, but we don't. Well, it's not a foil. It's an ink that we would apply.
It's process. Yeah. Okay.
Yeah, but we don't do that too much anymore. But what we do though is what we call a Tatsuta film. Tatsuta EMI shielding film PC 5600. And this is great because it's a really good shielding film. It's like a film. Okay, just like your Coverlay, it's a film.
Mm-hmm.
And let's say you have a 2-layer copper flex. You have copper and copper, and you apply cover coat on both sides, and then you just apply the Tatsuta on each side. And what you do is this is the Tatsuta film that I have, and you can see you have stitch vias on the side,
Mm-hmm.
and you use the stitching vias to connect your shielding film with your copper. Yeah, there's a possibility. Yes.
To shield Flex PCB.
Right. When it comes to finishing, pretty much all the finishing you have on PCB, you can also do on your Flex as well. But immersion silver and OSP probably not the best idea, simply because they corrode or they oxidize very easily, and you probably going to do a lot of Flex. Flex would probably be in an environment where you have people touching it and stuff. So probably not a good idea, but ENIG is the most common. ENIG and Hassel are the most common. So most of the things that we do is actually ENIG. Okay. ENIPIG is also getting quite, I wouldn't say common, but famous. But the thing with ENIPIG is you use ENIPIG for wire bonding. So if you're going to be using wire bonding, then ENIPIG comes in handy. That's with the palladium.
So it means someone is connecting Flex through wires somewhere?
Either you are doing that, or you're using wire bonding on your Flex somewhere. So you can have an area on a Flex where you're doing some components, and you say, I want to do wire bonding here. Then you would need ENIPIG.
What about the gold fingers? Do you need to do something special if you would like to use them on your Flex PCB?
Gold fingers, a lot of people use gold fingers, yes. And every time you have gold fingers, you want to have extra gold there so that they become hard gold fingers. So yes, a lot of, it's nothing special. You do exactly same as you would do on FR4 boards. But a lot of time we actually use ENIG on the fingers. So if you're going to have a Flex board that's going to go in and just sit there, unless you're taking it out multiple times like a USB stick, you don't need hard gold finish. Hard gold finish comes in handy when you have multiple inputs and outputs on those gold fingers. So
so for standard FFC Flex cable and connector, just use ENIG and that's good enough.
ENIG is probably the best, yes.
Okay, I didn't know this. I was not sure if I have to use like this hard gold. I don't know.
Right. I mean, hard gold, again, hard gold, if you're going to be taking it out and putting it in multiple times, then hard gold is great. But if you're just going to insert one time or few times, then ENIG is sufficient. So. Okay,
that's good to know. Next, what do you have next here?
Here are a couple of IPC specs which apply to, Flex World, right? So you can see these are related to Flex manufacturing.
Okay, base materials and base dielectric, no copper. Okay, so there are different materials.
Right.
Okay, how do you do 4-layer Flex PCB? It's you just put there copper and then the PI material and copper PI that's how you build it? It's not like core and pre-preg or something. You just put every single layer and then stick it together.
Right. Well, yeah, it's just like FR4. But I mean, if you have a standard Flex and you say it's a 4-layer Flex, and instead of using FR4, you're using a PI material, right? You have a PI material with copper and copper, so you have a design and design.
So you have some kind of core? Can you buy some kind of core for Flex?
Yes, that's exactly what it is. So we don't call it a core, but it's a polyimide material. So you have copper on both sides. So it's called a polyimide material, and you have copper on both sides. So just like a core, you would do your regular processes and designs on polyimide, which is like a core, yes.
Can you do 3-layer PCB?
Very common to do 1-layer and 3-layer in Flex world. And when it comes to PCB, nobody wants to build odd layers, because if you're doing a PCB odd layer, doing an odd layer is actually much more costly. In Flex, doing odd layer, like 3, 5, or whatever, it's very common. Very common. For example, I give you an example. This is actually a 1-layer circuit. This is a Flex, and there's nothing on this side, so it's just 1 layer. But then I have rigid FR4 attached to it, but it's not a rigid Flex. It's actually a rigid board attached to it, bonded. So what do you call this? This is not a rigid Flex. This is not a stiffener. This is a real PCB. So you have 1 layer of Flex, and you have, I don't know, maybe 1 layer or 2 layer of rigid PCBs attached to it.
How
so
do
you can have
attach it?
Using adhesive, thermally bonded. So you would actually attach this Flex with the FR4 using adhesive specifically for bonding these two. Bonding FR4 and Flex.
So the bottom layer of this FR4 is with no copper. It's empty, correct? And then you connect the signals through vias.
Yes, it's a 1-layer rigid board. Yes.
Okay.
And you're right. It's using the vias to connect on the other side, or these big holes right here.
I have a question.
Yeah, sure.
What are the layer limitations and maximum thickness limitations?
We have done Flex, which is like 8-layer Flex. So the limitation, it's hard to define in terms of exact numbers, but what I would say is, depending on what you're designing, if you want to bend it, and if you do your calculation and you think it's not possible to bend it, then that's your limitation, really, when it comes to Flex. I don't have an exact number, but all I can say is I think you can go 8-layer, you can even go 10-layer, as long as you understand how much bending you will be doing. That's if you're following the rules.
So theoretically, you can build any number of layers. Problem is, it will not be Flex anymore.
Right. I mean, that's how I see it. Someone may disagree with me, but I think there's no limitation on how many you can build. But at a certain point in time, you will say, well, what's the point? Because I'm not bending it anymore. So why am I using rigid Flex?
But there are some advantages, because you can place the layers much closer than on standard PCB, for example.
That is true. There are a lot of advantages as well for Flex, even though it's hard. Like, for example, something like this, it's very hard. Like it's bendable, but it stays in shape. So this is 10 ounce copper. There is, like, as you can say, the shape is also funny looking. So it's probably going somewhere where it's sitting like this. So, something like this, which is following the shape. So could be where you're using the Flex, or it could be, could also be some other issues as well. There are a lot of benefits. Like, for example, Flex circuits are really good when it comes to environment where you may have shocks. You may have like vibration or something. So if you have PCB versus PCB and you're connecting them, that could have, that could be replaced with Flex, rigid Flex, right? That's one. With the Flex, it's easier to handle the way the Flex materials are. It's easier to handle tighter spacing on Flex material than it is on a rigid PCB.
What does it mean? You can make thinner traces, for example, or?
Yes. So like if like we use 2 mil line width and spacing on a flex board using 1/3 ons on a mass production level, but I couldn't do that on a rigid PCB. I mean, I have worked on PCBs with like 2.5 mil spacing before, using 1/3 ons copper, and it was very challenging. But in our factory, we run 2 mil line width and spacing on mass production orders using flex 1/3 ons all the time.
Wow.
Okay.
And why is this possible?
All I can say is it has to do with the way the material is made. It allows us to handle much better. But the way I see it, also the copper that is used on flex material is not the same as copper used on the rigid board. The copper used on flex material is much more softer. It's a softer copper. I don't think it affects the 2 mil line width spacing, but it adds
maybe etching is easier or something.
I guess so. You can say that. Yes, etching is definitely easier on polyimide material. Yes, so it allows us to control thin line width spacing much better on flex than on a rigid board. So there's definitely a benefit.
Okay, we can continue in this. What is on the next one?
Maybe we want to talk about a little bit more about the stack up, if you don't mind.
No, yeah, okay, we can.
Right? Okay. So the important thing to consider when you're making your drawings and you're specifying your stack up is that you got to keep in mind that, you know, for example, like if you look at my slide, all this over here is for the rigid part, right? This is rigid. And this part right here is for flex part. And this is area right here is for flex with a stiffener. So a lot of time what happens is when I see designers sending their stack up to us, they do not realize that there's a little difference between flex with stiffeners versus rigid PCB. And let me share with you the difference. You see, it says here copper plating, right? But you don't see any copper plating here. Now, excuse me, it's possible that you may have some kind of components over here. Not possible, it's probably you have components that you're going to, either a through hole component that you're going to mount, right? Like the example I showed you before. So you have through hole components and it's just rigidized and you have a connector. Now, the thing is, if you have through hole components, they must have plating in them, right? But you don't see the mention of plating here, and you see the mention of plating here. This is a very important point I want to share. When you're making your rigid PCBs, you apply plating all over your PCB, right? Like if I'm making a panel, I am doing plating on the whole panel. Now, in the end, you etch off some of the copper plating that you don't need, but that way you end up creating plating inside the hole. If you do that on flex circuits, when you bend the flex circuits, that copper plating will crack. So that's why we don't have any copper plating on any of the flex area. The copper plating is only done inside the holes, and we call that button plating. Okay, so on a flex board, the plating is only inside the holes or around the holes a little bit, maybe 2 mils around the hole. Yeah, so there's no plating on any of your flex, because if there was a plating, when I bend it, it will crack. The only copper there is the material, the copper material, the polyimide material with the copper. Okay, so this is actually referring to the plating all over the place. This is referring to plating only on the copper, only in the holes. So what happens is when you're defining your stack up, you got to keep in mind that over here, you're adding a copper plating thickness in your overall thickness, of your flex, of your rigid area. But when it comes to flex, you're not going to be adding that thickness. So when you talk about flex here, there's no copper plating added anywhere.
But if there are, for example,
well,
pads,
I mean, no, right.
And when you do the copper plating for whole PCB, how do you need to cover these pads, or I don't know how you manufacture it.
Okay, let me show you. Let's say this area right here. This is a component mounted here, right? Mm-hmm. So the plating is only inside the holes, not on the pad. The pads may have E-ning, yes. Let's say you have SMT pads, right? So you E E-ning, yes, but you don't have copper plating.
So
copper plating is only
during
done
the plating
the
you cover it, or how do you do it?
Yes, that's right. Okay. That's right. During the plating we cover everything. Only the holes are open. Mm-hmm. So when you're defining the thickness of your flex, you gotta remember there's no copper plating on anywhere on the flex. Copper plating is only inside the hole. Mm-hmm.
So does it mean the holes are a little bit going
higher, thicker?
Higher, yeah, okay, that's what I mean.
Yeah. Right. So, but you don't see that on a PCB because everything is plated at the same time. Mm-hmm. So you don't see the height difference. You see it on the flex PCBs, on the flex circuits. Mm-hmm. So that's something I want to point out because a lot of designers are not aware of it, and when they start to define their flex stack up, they end up missing. Either they end up using that extra 1 ounce plating per side and they add it in their flex stack up, or if they're aware that there is no plating, they remove it from the stack up, but they still have to remember that wherever the plated holes are, they're going to be a little bit thicker.
Mm-hmm. I didn't know that. I didn't know you don't do copper plating on flex.
Right. So only in the holes and around the holes, maybe like 2 mil around the holes. That's where you will have the copper plating.
So if you create like 4-layer PCB, can you do like buried vias?
If you do PCB or flex?
Flex, sorry. Or there are always through-hole vias?
Well, you can, but the problem is when it comes to filling, because you would have to, in most cases, fill those vias. Mm-hmm. When you fill those vias, you planarize the surface a lot of time. You can't planarize the surface on a flex because when you're planarizing the surface, the flex is so soft that it rips apart. So that's why a lot of time we don't do buried vias on a flex. Plus, if you have a flex, it's just so small, it's so thin, then it's hard. But like, if your requirement is not fulfilling the holes for whatever reason, I mean, there are times when you don't fill the hole, then you can do buried vias. Mm-hmm. Okay, but it probably wouldn't be a via. It probably would be, some kind of fill holes, like the big holes maybe. Mm-hmm. But I like we do filling of the vias or buried vias mostly in the rigid areas.
What about micro vias on flex?
Micro via you can, yes. Micro vias you can, especially if you're doing it from layer 1 to the next layer. But again, if you do a micro via, you just have to make sure, does it require filling or not? A lot of time it doesn't require filling. So if you have a micro via and it's supposed to be like an HDI board, let's say that your micro via is supposed to have filling because it's, you're going to place a component on it, then it's not possible because if you want to place a component on top of these micro vias, they have to be planarized.
Yeah, I understand.
You can't do that. But we do micro vias all the time where we have micro via and we fill it with copper. Mm-hmm. It's just when you look at it, it doesn't look that good, but it works.
Mm-hmm. Okay, I understand. That's good to know. So in this presentation, you have these basic rules: trace and space, 3 mils, 75 micrometer. Okay, that's like minimum.
These are like standard rule. Like if trace and space, I'm saying here 3 and 3. That's like, if you make it with 3 and 3, that's like the most beautiful design. I don't have to worry about anything. But let's face it, most of the time, you're not going to be dealing with 3 and 3. You probably a lot of time I see design with like 2.5 mil spacing or 2 mil spacing. But yes, I mean, if you have space, it's good to design with 3 and 3.
But you know, I would really worry that this is going to break, because it's like, it's super thin, isn't it?
All flex are like that. Most of the flex we do are 3 mil.
And it doesn't break. Wow.
No, it doesn't. We just made a flex circuit for a company which is going to be doing some testing on their material. And we made this flex circuit, and they told me that they're going to do a 1 million bend test on it. They're going to be bending it 1 million times to understand how their material is behaving, right?
Interesting.
Yeah.
Okay. Any other rules, like, I don't know, minimum via, minimum hall?
So when it comes to flex circuits, okay, yes, I do have something very important to share. So flex circuits, most of the time, you know, on the flex, we do laser drilling. A lot of time, the vias that we are doing are laser vias as well. So if you're doing a laser via, 4 mil via is very standard.
Mm-hmm.
Okay, 4 mil via, no problem. 4 mil, sometimes you can even go 3 mil, but that's a little advanced, but it can be done. 4 mil vias, so if you're doing laser, and most of the company who do laser drilling, they also have what they call LDI technology, laser direct imaging, for imaging their panels, which allows you to
drill into center.
Well, yes, but also you don't need like 5 mil annular ring to make sure. Yeah, well, laser drilling allows you to have a very high accuracy, but the laser direct imaging, which is a technology for doing your design on your, you know, replicating design on your flex circuit itself, is also very, very accurate. So what happens is, if you're doing a regular PCB, if you're not doing laser, if you're doing mechanical drilling, then you have higher tolerance. So you need higher annular ring, like 5 mil per side. With the laser, you only need 3 mil. So if I'm doing a 4 mil laser drill, I only need
3 and 3, 6 extra.
So 10 mil copper pad. Okay, 10 mil copper pad. That's all what I need. Okay, so you have 10 mil copper
3
pad.
And 3.
Yes, 4, 3, and 3. Yeah, that's right.
Okay.
So that can be done on flex, because a lot of time we use laser. But here's the thing: when you do rigid flex, okay, when you do rigid flex, now we talked about it. Rigid is mostly 5 mil per side, right? But the problem with rigid flex is that rigid material and your flex material are two different materials, and they have different CTEs. So the expansion could be different. So when you connect your flex with your rigid, you want to have extra copper pad around your hole to ensure that you're compensating for that, higher variation in expansion. So what I would say is, in that case, you would add, instead of having 10 mil pad, you probably want to go with 12 mil pad, extra 2 mil.
Extra 2 mil, okay.
Extra 2 mil. So that, 1 mil extra on each side will kind of compensate for the difference in expansion for different materials.
In the area where the rigid board is located, you would like to use 12 mil vias instead of 10 mils, and on the flex itself, 10 mils.
That's right. That's right.
Okay. Yeah, I think these are two most important dimensions: trace and space, and via.
Right. The next slide is about panelization. Okay. I'm not going to spend too much time, but I just want to cover this because a lot of time people ask, why is their flex so expensive, right? So it comes down to how the shape is and how I'm putting them in my panel. I mean, this shape, as you see, I can nest them, and I can rotate. So one is like this, one is like this, and I can get more per panel. But not all shapes are like that. So depending on the shape, I could be putting 1, 2, 3, 4, 5, 6, 7, 8, or I could be putting 800. Doesn't matter. I mean, you know, it all depends on the shape and how tightly can I put your circuits on my manufacturing panel, and that's what determines the, you know, the price. A lot of people don't realize it. They're like, oh well, I have just this, you know, simple, but it's the shape and how many I can put in a panel.
Mm-hmm. You know what?
Right.
What I keep thinking about is like the flex is very flexible. So how do you actually keep it kind of rigid when you are going through all this manufacturing process?
That's a good question. That's a very good question, actually, because that's the problem we deal with every single day. So when you're doing a flex, yes, you know, unlike PCB, so if you ever visit a PCB factory, you will see, let's say you have a job and it's 10 panels, and you will see people carrying 10 panels like this because they're rigid. Flex, you cannot. So we use special, I want to call it a binder or holding, something to keep the panels rigid. So these are very rigid. They're like books, you know, large books where you keep the panels when you're transferring them from one process to another. But at the same time, then you get to etching process and film stripping process, and it's a big problem, because when these panels, you have to put them on a conveyor belt, and you know, they slowly go to these machines, and it's very easy for them to bend down and go inside the machine and destroy themselves. So that's why we have to do these special, we call them fixtures or special leaders. We will take a regular FR4 board and make a frame out of it, and we will attach these frames to these flex panels, and then we run them through the machine. But yeah, I mean, that's a good point you brought up, because it's definitely something we have to fight for every day. It's not easy. They're the flexible panel. They tend to get dense easily on them. They tend to go like, you know, they bend easily. And when they bend, they create dents, and when they bend, they warp. It's very easy. So they're very sensitive for sure.
And then basically, stiffener is kind of the last part you place on it, because then it's hard to, I guess, manipulate. And the last process will be cutting out this, because I guess once you cut it out, you are not going to do anything else with it.
Well, I would say this: the hardest, not the hard, but once you apply the coverlay on your panel, then the process becomes easier.
Oh,
even
okay.
Even if they are flexible, once you have applied the coverlay, it's done, and you're like, I'm finally happy now, and because it becomes easier. Now, when it comes to applying stiffener, sometimes we apply stiffeners while the flex panels are in panel forms, and we apply the stiffener and cut them later. And sometimes we cut them first and apply the stiffener later. It depends on what the requirement is. It depends on the shape. Okay. So yeah, that's what it is.
How this is done? Because if you have stiffener only on the end of the flex, for example, does it mean you glue this small piece of the stiffener on this place, or I can't imagine how it is done actually. I don't know.
Well, what it is we use adhesive, and then let's say you cut the board already, okay, and you want to apply the stiffener. So we apply this special adhesive, and we don't, and then we put the stiffener on top, and you apply a little bit of heat, just a little bit of heat. We have special heat plates. You apply that heat, and that adhesive starts to bond the stiffener with your flex. But it doesn't mean it's thermally bonded. It's just barely bonded. And then we will create these special fixtures, and we will place these flex with the stiffeners in these special fixtures. And then we will take them to the pressing machine, And that's where you press them just like you press a material for a specific temperature, specific heat for a specific period of time. Then those stiffeners become really thermally, they become really, really bonded with your flex.
So you create these fixtures for every flex which is created with stiffener after it is cut out?
Pretty much. Pretty much.
Isn't it like expensive?
It's expensive. That's why flex circuits are expensive. There's a, in flex, there are a lot of manual process, and a lot of manual process is around the stiffeners. Okay, so it ends up being very costly. So like you could be asking, oh, I just want to apply a simple FR4 stiffener, but the cost of applying a simple FR4 stiffener could add maybe 20% of the cost. I don't know. I mean, it depends on how big the board is, but that's what it is. I mean, applying it is very easy, but doing it properly on a mass production, the way you create your fixtures and stuff, it could be very expensive.
And if you apply stiffener when the PCB is still in the panel, how you do this? Because then it will be only pieces of stiffener in some specific places of the panel, or?
Yes, but we still have to create a picture for it. So we will create a picture where we will cut those stiffeners that we need, and we will place them on that, at the location, and you put the whole panel on top, and then you do the same process. Wow. It's the same process. Of course, if we have the luxury of doing it in a panel form, we apply the stiffeners and do the flex in the panel form is easier versus applying the stiffener on individual pieces. But without getting too much into the details of manufacturing, there are times when you do stiffeners in a panel form, and there are times when you have to do it in the one-up.
I thought there is some special trick like how to do it, because this was my first idea how it is done, like complicated, and I thought like, oh, they can't do it this way. It looks like you do it this way.
especially when you have a stiffener on both sides of your flex, and not just both sides, like. You have a flex, so let's say you have a flex and you say, I want a stiffener on this side on top and a stiffener on this side at bottom. That changes everything. So that adds a lot of cost and a lot of manual process.
That's good to know. Then if someone would like to use cheap flex, no stiffeners. And that's everything. Thank you very much to Ata for helping me to create this video, and thank you very much to you for watching. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.